See and hear me?
That's it.
My corner, can you confirm that you can see me at the moment?
They will occupy a good chunk of space we see.
Okay. So I've been dealing with prime numbers since '96, I think it is, and discovered something rather interesting about prime numbers exactly 10 years ago in 2012. I did a little bit of work on the periodicity of the prime constant. That's all online now on archive. And it was about 4 or 5 years ago I decided to use my entropy function to investigate the relationship between entropy and primality. And I got a whole paper out of that and discovered some really interesting things. And as a result of that paper, I decided to take it back a little bit and go back to basics. And this is what I'm now going to present. I think last year I had a go at doing it, but my thoughts were very untidy. But I've had a year to work on it, and this is where I've got. And I've actually got some interesting results that well, I think they're interesting, hopefully you will too. So we're going to talk about periodic numbers. Interesting to hear just earlier about periodic Minkowski spaces. I wonder if there's a relationship there. We discovered periodicity through the binary derivative. That was some work done by Mervyn Nathanson 50 years ago, and still hugely relevant. And so I've got 5 theorems from that. So I've actually formalised the work rather. Then I introduce a metric which I call PS prime, where we talk about the probability of either being prime, the probability of being a prime number, or probability of not being a prime number. I've got some empirical results, and I sort of map out a little few things that I need to iron out over the coming months and years. So a periodic number is some string of length 2n. It's in 2 parts. We can call them part A and part B, the left part and the right part. And so you can see I've got an 8-bit string down here, 1101, 1101. It's a periodic string. 73, 73, 73, 73. That's an incredibly important number. Does anyone know why? It's the first 6 digits of which are is my local pub. 01449 73 73 73.
Have you published that?
Okay, so the string, a periodic number can be in any base m. And so the proof is high school arithmetic, and so you can see that the reasoning is very simple. Since a is greater than 1, because we're dealing with numbers a greater than 1, k is composite. So the proof that a periodic number in any base is composite is extremely straightforward, but very important. So every time you see a periodic number, you'll know that it cannot be prime. And there's one exception, which is where a equals b equals 1, where the number is of the form 1, 1, 0, 1, 0, 0, 0, 0, 1, and so on. Every number can be written as 1, 1. So for example, 23, which is prime, can be written as 1, 1, because 22 plus 1 is 23. So all the natural numbers can be expressed as 1, 1 in the base that is 1 less than the number itself. But there are some special numbers of the form 0, 1, 0, 1. These are the Fermat numbers. And I speculate that n to the y plus 1 for y greater than 2 is probably composite. It's empirically composite for some m and y up to about 10. But I haven't had the time to explore whether or not m to the y plus 1 for y greater than 2 is in fact composite. So here are the 8-bit periodic numbers. There are 16 of them, because there are 16 numbers between 0 and 16, and surprise, surprise, we find that just by investigating periodicity, we've suddenly discovered the 17 times table. So how's about that? And so you can here are the 8-bit primes. So the numbers between 0 and 256 that are prime marked with a 1, and you can see that on the diagonal, which contains the periodic numbers, there are no primes, except for this one, which is 17, which is a Fermat number. So, 17 is a periodic number, or I thought it was until this year. But we come now to what are known as the n-periodic numbers. So if the left part is the 1's complement of the right part, AB also cannot be prime. The proof is just a little bit longer than the previous proof, but it is a proof, and it's incredibly straightforward and simple. So here are the n-periodic numbers, 8 bits long. And hey presto, we've discovered the 15 times table. Well, we haven't done any division yet. All we've done is laid out the periodic and the n-periodic numbers. And then we have the z-periodic numbers. They didn't exist until this year, because I suddenly noticed that what about these numbers that have got a 00 at the beginning, or a 0000 at the beginning? How does that relate to their primality? And so the proof that ZAB cannot be prime is trivial, because of course we simply remove the Z, which has no numeric effect on the string, and theorem 1A follows automatically. And of course it's trivial, but ABZ cannot be prime either. Would anyone like to tell me why?
It's the zeros.
Yeah.
There are twos, right?
Correct. Yeah, the numbers of the form ABZ are all even numbers. So apart from 2, none of them are prime. So these are the Z periodic numbers with 4 leading zeros, Z periodic numbers with 2 leading zeros, and look at this, we've discovered the 9 times table. Just by investigating periodicity, the 9 times table pops out. And here are the Z periodic, N periodic numbers. Firstly with 4 leading zeros, secondly with 2 leading zeros, and we've now discovered the 7 times table. So the issue of primality and compositeness is intimately related to the periodicity and of various forms found in a number. So when I was first investigating this, I came across the binary derivative. I wondered if by computing the binary derivative, which is simply the exclusive OR of the string, whether or not that would help to discover the periodicity. And indeed it does. There's a beautiful paper by Mervyn Nathanson in 1971 on periodic numbers and binary derivatives. So there's n-1 derivatives and n-bit string derivatives. The string itself is known as the 0th derivative. So I show here d1s, which is the first derivative. So 1, 1, 0, 1, 1 gives 0, 1, 0 gives 1. So if to do the derivative, if the numbers are the same, they generate a 0. If the numbers are different, they generate a 1. And so that's how we do the binary derivative. So these are 2 very important theorems, and they underpin all this work. So for theorem 2, which is due to Nathanson, a binary number S comprising the digits S1 to Sn is periodic with period 2 to the power of n, if and only if for some k between 0 and n, a derivative is 0. So by looking at whether or not any of the binary derivatives are 0, we gain information about whether or not a number may or may not be prime. And importantly, due to Davis et al., the derivatives are uncorrelated and are statistically independent of each other.
So can I just check there? So the d subscript k is doing the derivative k times. Is that right?
Yeah, the first derivative is, the string itself is d0.
Right.
First derivative is d1 of s. Second derivative is d2 of s, and so on.
Just checking it.
So the successive binary derivatives are statistically independent of each other. You'll see how important and how interrelated all these theorems become shortly. So theorem 5, every binary number is the binary derivative of exactly two numbers one bit longer. So every number in binary is intimately related to two other numbers. So no matter what the magnitude of the number, it's always got two close relatives, and the binary integrands are one's complements of each other. So the proof is again trivial, many of the proofs in this paper I do by example. So here we have 0, 0. The first derivative of 0, 0 is two zeros. The first derivative of 1, 1, 1 is 0, 0. So as you can see, both forwards and backwards, the 8-bit numbers are pairwise intimately related to 4 2-bit numbers, which are the binary derivatives. Okay, and so this happens no matter how big the binary string is. They each have these two intimate relations. And finally, another trivial theorem, theorem 6. If a derivative is all ones, then if a string is all ones, then its first derivative is 0. For example, earlier I said we were looking for if a derivative was all zeros, then the string may be periodic. Well, in conjunction with theorem 2, theorem 6 tells us if a string is all ones, then it's potentially periodic because its next derivative is 0. So we can now construct a probability metric, and I've called it PS not prime. So the probability that S is not prime, let PS prime be the probability the number is not prime due to its periodicity, its n periodicity, or its z periodicity. Conversely, PS prime is 1 minus that number, which is the probability that a number is prime. So, which is an interesting. So, if you give me a number, I can tell you what the probability is that it will or will not be prime based upon the patterns observed in its binary derivatives. So, there are 256 8-bit numbers. 16 of those on the diagonal of that previous diagram are the periodic numbers. 16 are n-periodic numbers, and 22 of them are z-periodic numbers. That adds up to 54. Well, in fact, there are a few duplicates, but I'll set it out like that for now. So for the 8-bit numbers, the PS prime is 0.21. So the probability of not being prime is the probability. I've got that the wrong way around. The probability of S being prime is 0.21, which is because there are 54. I'm getting myself confused. So the probability of not being prime. So these numbers can't be prime. There's 54 of them. So the probability S the probability S not being prime is 0.21, and the probability of S being prime is therefore 1 minus that, which is 0.79. The reason for the confusion is that there are also 54 numbers that are prime, less than 256. So the number 54 is very familiar to me. So if a number is periodic, n-periodic or z-periodic, the probability of it being prime is nil. Yeah? Otherwise, if we can construct a very simple weighted average of the fact of whether the derivative is 0 or not. So we define a variable called zk of s, which is 0 if the derivative is 0, otherwise it's 1. And so ps prime is simply the sum over all the derivatives and the string itself of whether or not the derivative or the string is 0. That's the weighting. So ps prime is an hierarchical weighted average of the fact that any of the 2n minus 1 binary derivatives of s are 0, and ps prime runs between 0 and 1 inclusive. Any questions on?
Wait, is that PS prime or PS not prime?
Both. They both run between 0 and 1.
No, I mean, but here's the title says the probability of not being prime, and then you said PS prime. An equation for
I'm doing both. I'm doing both at the same time.
But your equation, your big equation
is the probability.
that is S prime.
Yeah, the probability of being prime.
Okay,
So I write here PS prime is the sum of. I'm writing here PS prime is ANPA.
Yes, I know. You go 1 minus 1 is 0.
One minus the other. Yeah. But in the rest of this analysis, I wrote. The property comes from being able to investigate because you know that if a number is periodic, it cannot be prime. So that's where it stems from. But it's a greater utility to use the probability of using its converse.
I see. Okay.
Yeah.
Yes,
Good question. Good point, though. Okay, and so this is the simple calculation of the calculating PS prime. So starting with the number 23, which is prime. It's not a periodic number. So in fact, but it is a z periodic number. So PS prime should actually be zero. Not the best example, is it? This is why we do these things. We find out our own mistakes. Yeah. But we can still calculate the PS prime. So here's the string. Here's the first derivative, the second derivative, third, fourth, fifth, sixth, seventh, and final derivative. So here's the number of 1s in each string, in the derivative. This is the length of the derivative, and this is the z, whether or not it's all zeros. So it's only the last derivative that's all zeros. And so here's the computation that we get to. And theorem 6 is really useful because all the whole calculations are just off by a small amount. So we add in the Mersenne probability, which makes all the numbers convenient proportions, which is extremely useful for us. So that's how to calculate. And so there we have the first 256 numbers laid out according to which number it is. So 0 is there, and that has a PS prime of nil because it's periodic. You can see all the periodic numbers down the middle. This one here, it looks like a periodic number, yeah, but it is prime. It's 17 because it's Z periodic. So if you take the first two digits off 17, you're left with 010, 001, which is aperiodic. Therefore, it can be prime, and indeed it is.
So could you explain the colour coding?
So So 0 is white, 0.25 is yellow, 0.5 and 1 are in orange, and the prime numbers are marked in purple.
Right, great, thank you.
Right? So you can see that there's only one prime, but something is
Right.
white. So we can extend the prime number theorem. So the number of primes less than s, due to the prime number theorem, which is Hadamard and de la Vallée-Poussin of 1896. Number of primes less than s is the s. It's a logarithmic integrand of s. The number of actual primes less than s is called pi of s, usually written with the pi sign. I'm just writing it in text because it's more convenient. So if we can now modify or extend the prime number theorem by ps prime. So the probability that s is a prime number is approximately s times p of s. And I have, of course, investigated that. So here you can see in the columns we have numbers up to 16, numbers up to 32, numbers up to 64, and numbers up to 65,536, which is 1 with 8 zeros, 1 with 16 zeros after it. There are 6,542 numbers less than 65536 that are a prime. Lie of s, which is the prime number theory approximation to the number of primes less than 65536, is slightly different at 6584. Reasons which I won't go into. I'm dealing with pi of s at the moment. So you can see here a matrix setting out how many primes we expect by ps prime according to our theoretical model. And of course it was only, I'd never done this before until 4 months ago. So what do you think I found? It worked. So here are the actual number of primes by ps prime. So you can see that there's a fairly close correspondence. The correspondence is not exact, and that is the difference graph. So you can see that there's a fairly strong correlation between expected and actual, and there are two systematic differences. One is that there's a systematic excess in the number of actual primes that have a ps of 1, and that is exactly matched by the deficit in the number of primes that have a ps prime less than 1. And that's something I'm working on. The two at the top are the only two periodic primes, which are 1, 1, which is 3, and 0, 1, 0, 1, which is 5. So if we now graph the rows of these matrices, we can see that the number of primes goes up quadratically as the number of integers goes up. So 16, 32, 64, 128, is a quadratic expression. We can see that the number of primes goes up almost quadratically, as does the number of primes that have a ps prime of 1, those that have a ps prime of 0.5, and so on. So at all scales, up to 65536, we get the picture that we pretty much expect. And if we do a logarithmic transformation, we can see that the number of primes that are ps prime of 1, ps prime of 0.5 and 0.25 are essentially parallel lines. So these relationships hold at all scales, based on the evidence so far up to 65536. Now, this is an important relationship. It's a relationship between PS prime is 1.0 and PS prime is less than 1.0. It starts out way out, but gradually converges. It goes up a little bit here, comes out in a moment. But if we look at what our expectation was here, the relationship between the total number of primes, 6542, and here, 3271 is exactly half of 6542. 1636 is almost exactly half of 3271. 818 is half of 1636. 409 is half of 818. So what we're expecting is that the ratios between these pairs of terms stays at about 2 to 1, or the relationship between this term here, number of primes that have a PS prime of 1, matches exactly the number of primes that have a PS prime of less than 1. And this is what I'm trying to set out here. That it appears that this ratio is generally converging. This is the R squared between expected and actual. So we have the expected number of primes by PS prime and the actual number of primes. The R squared is converged already at 1.0. So there's a perfect correlation between the expected and actual. So this gives us an interesting nomenclature, which is numbers that have a PS prime of 0 cannot be prime. That's because they're periodic, n-periodic or z-periodic. Numbers that have a PS prime of 1.0, they may be prime, because no binary derivative is 0. Numbers that have a PS prime between 0 and 1 may not be prime, because one or more of the binary derivatives is 0. So it's quite useful if those definitions are quite useful because they're pretty exact and also very meaningful. You know, something cannot be prime because it's a periodic number. Something may be prime because no binary derivative is 0. Something may not be prime because one or more of the binary derivatives is 0. And then we can combine them in obvious ways. So the total number of integers less than 65,556 are divided into two types of numbers that can be prime and numbers that cannot be prime. The numbers that can be prime are divided into two categories: those that may be prime and those that may not be prime. And this ratio that I mentioned just a few moments ago, the number of numbers that may be prime approximately equals the numbers that may not be prime. Okay? And the ratio between those two terms, the may be primes divided by the may not be primes, seems to be asymptoting to 1. Okay? And so these are pretty important results. Because what we've done is we've set out a theory of how the primes are distributed. And the Riemann hypothesis is all about the distribution of prime numbers. Well, I believe I've just set out a fairly convincing case for how prime numbers are distributed in the binary domain. So now that we can calculate a number called PS prime for every integer, from here to infinity and beyond, we can reorder the number line into a different order, and we can change the order of the numbers of the integers into an order that's based upon the relative likelihood that they are prime. And so that's what I've done with the blue line. The pink line is a slow logarithmic curve, which is the actual distribution of prime numbers, and the red line is a quadratic curve fit to the PS prime density. So from here to infinity, in whatever interval I choose, whether it's a power of 2 or whether I do it piecewise, I look at the first 17 numbers, the first 18 numbers, the first 19 numbers, the first 22,271 numbers. Whatever interval I look at, because those 9 theorems are scale invariant, they apply at all times. There's basically no wiggle room in terms of how the primes have to behave according to these rules that are set into the mathematics of the binary derivative. So that the error between the red line and the blue line is bimodal. That's because PS prime is quadratic and it's in lumpy parts. This distribution is in lumpy parts. It's bimodal, and you can see the standard deviation is, well, the range is from 130 to 190, which is 320. So the standard deviation in the number of primes is just 55. And what we can infer from this is that the variation in the way primes occur is minimal. And in fact, in an earlier paper I showed it was in fact nil in the limit. The work I have to do now is go back to the big red line at the bottom is where the work is. So you can see the values are rather small. Then they start in the bottom right hand corner, 317. That's a statistically significant difference. The numbers to the left aren't statistically significant. So I need to discover what's causing that, if anything. So examine the difference between may be prime and may not be prime, and discover why it's not exactly 0. I've got a clue there. Probably relates to the tension between the logarithmic number of primes and the binary doubling. As you double the number of primes, as you double the number of integers, as you extend the number of bits by 2 every time as you add a bit, the number of primes doesn't quite double because it's logarithmic. So I'll be examining this again empirically in C up to 32 bits, and maybe I can find an explanation about the anomaly I've mentioned by working in trinary. So that's that big red line on its own. So you can see it was quite a big jump, and again it's re-expressed there in purple. The blue line is behaving as it should, which is the number of numbers that cannot be prime as a fraction of the total number of numbers. So there are 8 numbers, i.e. half of them less than 16, that cannot be prime due to the periodicity, whereas by the time we get to 65,536 there are about 1,000 numbers that cannot be prime due to periodicity. So that blue line behaves as expected. It's the purple line which I need to do some more work on. So what I've done, I've introduced a scale invariant theory of periodic numbers. So 9 theorems that apply at all scales to all integers, all circumstances. I've demonstrated that the primes largely behave according to these theories. So the primes are aperiodic, which I don't think is widely known. I've also shown how some interesting integers pop out when we investigate periodicity. provide a small manipulature around the primes, maybe prime, maybe not prime, can be prime, cannot be prime, and reaffirmed my earlier published work that prime density can be quadratically explained with a very small, or in fact zero variance. That's it. Thank you.
Can we have the rogue salary up, please?
Participants? How do we do that?
No,
I don't know.
you go to stop share event only.
Sorry? Oh.
So thank you very much for that, Grenville. Hold on.
I have a couple of
Can I have
observations.
a very simple question?
Sorry, can we have a...
Hang on.
just a minute, can we have one very simple question from Barbara?
As a non-native speaker, I find it very hard to distinguish between cannot and may not.
Okay.
Yeah?
Cannot is absolute. If I lock the door, if I lock the door, you cannot leave this room.
Okay.
So I've locked it with the key. If I leave the key in the lock,
Okay.
you may or may not leave the room.
Okay.
So it's absolute. One's absolute and the other's relative.
That's what teachers used to say, isn't it? Can I have a pencil? You can, but you may not.
Sorry, Mike.
Mike?
Thanks again, Grenville. Two observations.
Go ahead.
The golden ratio appears a lot in nature,
Yeah.
and if it's expressed as a continued fraction, it is all ones. I wondered if this, to some extent, would tie up with what you're doing. Have you ever looked at that?
Expressed as all ones. Explain. I know the golden ratio.
As a continued fraction.
Okay.
1 over 1, 1 over 1 plus 1, and so on and so on. Anyway, let me leave that.
Yeah.
The other point is to do with your pink line going up at 65536.
Oh yeah.
This allows us to refer to the combinatorial hierarchy, which so far has been ignored. If you remember, Frederick's invention tweaked the ideas of Clive in particular as to why it was that the process is terminated, and it's when the label space is 65536 and the required number is 10 to the 40th, more or less. So it seems to me that there's something funny which may relate to the combinatorial hierarchy.
Thank you so much for that. That was extremely valuable.
Okay.
Thank you.
Okay.
Just remind me again that in the combinatorial hierarchy, one of the cut-offs was 65536. Or are you speculating that 65536? I can't remember the theory in detail.
The claim is that it's a hierarchy, and if we use Frederick's idea that you start with an empty space and you pull in something which is different to what's in there, then you need a new, if you like, distinguishing set, and it increases 3, 7, 137, and then it goes to, roughly speaking, 10 to the 40th. But you've only got 65536, 256 squared labels. So the scheme of Frederick's terminates at that level. And I've never seen a satisfactory notion there, but it may tie up with why 4-level hierarchies are so common in nature.
Yeah.
Things like data, information, knowledge and wisdom, and objects that must be 3-dimensional can be points at the next level and stuff like that.
I can give a bit of there's a bit of insight there I can share. In Nathanson's theory, I'll just read it. I'll just read it out. I think it's theorem. It's theorem 2. A binary number S is periodic with period 2 to the n if and only if for some k between 0 and n the derivative is 0. Well, in a first in the first writings of the paper in this presentation, I left the expression with period 2m out of that theorem. And then as I was going through investigating and testing, I noticed, hang on, there are numbers here that are where the derivative is 0, and or not 0, and the numbers are periodic or not periodic, which is in contradiction to theorem 2. And it was only when I reread Nathan's work that I noticed again that for several years, and in the previous paper, I'd missed out the qualification with period 2 to the n. So the discovery of periodicity with period 2 to the n, which is of course related strongly to 65536, could be critically important. Thank you.
Continue your work. We look forward to new theorems and results next year.
Yeah, thank you.
Right.
Any
Questions?
You may have shown, but I think maybe I missed it. Did you have a graph with the proportion of numbers that may be prime, that are prime, and the proportion of numbers that may not be prime, that are prime?
No, I haven't got that one on.
Okay.
It's easy. It's easy to do.
Okay.
So
I'm just wondering how powerful that distinction is in terms of.
Yes, there's a graph. The graph. There was a graph of may be prime that divided by may not be prime. So that,
No, not that. I want the proportion of prime and maybe prime divided by maybe prime. In other words, you have two classes, right? You have two classes that you have the class that may be prime and may not be prime. Right?
Yeah.
Those two classes. I'm just wondering about the relative distribution of primes between those two. Is it more likely to have primes in one than in the other? I mean, is that a...
No. May be prime and may not be prime.
Yes.
Seem to asymptote to 1.0, so the same number of primes in each.
The same number, but that's not my question. My question is, how many of the may be primes are actually prime? And how many of the may not be primes are actually prime?
Okay, got it, yeah. So looking at the denominator. Yeah, I've got it. Yeah,
Okay.
I can do that graph offline for you. Yeah. I've actually got I've actually got the worksheet with me, so we actually run that.
Okay.
Yeah. Any other questions?
Any others?
Just impressed.
Okay, it's very good that, and very interesting indeed. And Gil's got a question.
Can you just go over when the LiveX came in to your presentation when you were using LiveX? I was just unable to follow at that point.
I should present the results both with pi of x and LiveX. I chose to do just pi of x,
Right.
and I just put li of x as a row on the bottom, just so that you can see it's very close. But that's a good point. It's just an economy of presentation.
I've got some announcements. I don't know where Andrew is, but we're going to go to the pen factory now for dinner. Those who want to go for dinner with us. Now, who wants to go on an outing tomorrow? Because we're thinking of going